start with a quick look at the graphical abstract and some relevant documentation. And I also have here the pictures from the graphical abstract, which I want to supplement with some keywords like benzene, it's easy to see where it is, graphene, resonance, aromaticity, pi and p orbitals, symmetry, symmetry labels, molecular symmetry and crystal symmetry, sublattice structure, crystal structure, and molecular structure. I actually have some to say about polycyclic aromatic hydrocarbons and nanographenes and graphene nanoribbons, and also about topological edge states or end states. The last part will not be covered in this talk because of lack of time. Anyway, I want to stress the fact that all we know for graphene, most of the people, is described by the crystal structure. Okay, I have some highlights here, and these highlights are also the conclusions of this work. The most important thing is that graphene, all the exotic properties of graphene, Dirac points, topological insulator, are clearly due to the competition between its molecular and crystal character. Actually, graphene has a nature, a dual nature, crystal and molecule. We are used most of the times with a crystal representation in K-space, and this approach is a different one, stressing the molecular structure, the molecular point of the nature of graphene. So here I have some conclusion that graphene is flat, stable, it's a resonance structure, and it's bottleable, which is some of the important properties to define aromaticity, which is a peculiar property. And also I want to stress that the molecular bridge, the route from benzene to graphene, consists of a sequence of hexagonal polycyclic aromatic hydrocarbon PAHs, forming the main sequences, as I have called it before, and sharing some common properties with both graphene and benzene. Okay, so I have to describe, first of all, the benzene. What we know so far is it has two resonant forms, and you know that before these two forms are equivalent. In fact, we don't have simple double bonds and double bonds, but we have delocalized pi bonds all over the molecule. We have two resonance forms. Okay, and this in the electronic picture, you can see it also as a distribution of pz orbitals in each corner of the molecule. You can see that better here. And there are 6 of them, and also you have localized sigma bonds, which are localized between the atoms, and these are sp2 hybridized, and the pi bonds, which consist of the delocalized bonds all over the ring. These are some properties of benzene, and I want to transfer these properties over to graphene. Okay. Try to say a few more things about benzene. The crystalline, what's the point here? Benzene it has a point group of D6H, which means it has a major 6-order axis, rotation axis, and almost about 12 other characters. It has also some, it has the pi orbitals. There are 6 of them. And as you can see here, the labels we use are, as we call, the names of the irreducible representations of the symmetry group. This is not so important here as to distinguish just 2 different cases. We have an index G here, which stands for Gerade, meaning symmetric, and it's symmetric with respect to inversion. And this orbital also is E, it has an E index here, which means it's two-dimensional. In other words, it's equivalent to two molecular orbitals, normal molecular orbitals, and therefore it can hold up to 4 electrons. So besides the U, and the U orbitals are odd with respect to inversion, they have odd parity, and the total number of them, if you count them, are 6, is an equal number of odd and even, and an equal number of one-dimensional and two-dimensional representation. So if you move to the next picture to see what we expect to be the levels, molecular levels of benzene, you see the description of benzene is in real space because it's a normal molecule. And this is what we are going to try to do for graphene, which up to now we have examined in K space like a crystal. So I want to see here the lowest orbital here, the A2U, it has no node at all. And this is why is the lowest energy orbital. The principle is the more nodes the wave function has, the higher the energy. So here, this orbital has no nodes at all, and therefore it's the lowest energy, and it holds 2 electrons, which spin up and down. The next orbital is the E1G. It's a two-dimensional, it's actually equivalent with 2 normal orbitals, and it holds 4 electrons. This, remember, this one has only one nodal plane, this one or this one. And this is why is next in energy for this one. This actually is the HOMO orbital, the highest occupying molecular orbital, as we call it. If you take E2G orbital here, you see that it has 2 nodal planes, 1 and 2, in the wave function, 1 and 2. And this is why this is higher in energy, and it's not occupied for graphene. It's the lowest unoccupied orbital. It's a LUMO orbital. If you have a look at this final orbital that we have not examined here, it has 3 nodal planes, 1, 2, and 3. And this is why it's much higher in energy, and we cannot see it here. So this is the molecular structure of benzene, and here I have shown you the same orbitals, but see with the PZ orbitals forming the PZ orbitals forming the pi molecular orbitals. Okay, so what happens to the aromaticity beyond benzene? Here I have a aromatic molecule. It's one of the smallest polycyclic aromatic hydrocarbons. It shares with benzene planarity, aromaticity, and symmetry. It has hexagonal symmetry. Its normal form, if you can write it like this. This one is the ball and stick picture. This is the chemical picture. What you see for this orbital, it is like it consists of a central ring of benzene surrounded by another layer of benzene molecules. And you can see that this gives you an idea of how to build the bridge from benzene to graphene. For instance, this is the next molecule, which is known as circumcoronane. Those are existing orbitals, are not just models, okay? The existing systems. And this one you see, again, it is benzene, the ring of benzene orbitals around benzene, which is a coronane, and then another ring, third ring, which is around coronane. This is why it's called circumcoronane. And this already tells you how to build the bridge. The next one should have another layer and another layer and another layer. But at this point also, I want to make another point that once we start building molecules around benzene, the carbon atoms for benzene are not anymore equivalent for this reason. let's consider this the red and blue nearby carbon atoms. And although if it was for one benzene molecule, they would be equivalent, here they are, because if you consider chirality, you see that here the red orbital has legs, and the blue atom, the red atom has legs, and the blue atom has arms. So the one is the image of each other, and therefore they are not equivalent once you start building more and more. And this is the same thing happens for every two neighboring atoms. This is known also as the sublattice effect. And it's known that the honeycomb lattice is not a Bravais lattice exactly for this reason. And this is actually the starting point and the main point for all these properties of graphene, that the symmetry of the molecule is not the same as the symmetry of the crystal, because in the crystalline place, these two molecules are not anywhere equivalent. I will come to this point. And so the next question is, once we have so many rings, can all the rings be aromatic, like it was for benzene? And the answer is obviously no, because each carbon atom belongs to more than one ring. For instance, this one is shared with 3 rings. And therefore, since the number of p electrons is equal to the number of carbon atoms, there are not enough electrons to cover every ring, and therefore some of them will be full or aromatic, and some of them will be empty or non-aromatic. Okay, so here is how to distinguish aromatic rings. We put full or empty circles in their center, and the pattern of full rings defines the aromaticity pattern. This is the aromaticity pattern of Coronen, and you can have it either this way or this way. They are both equivalent. So let's just state some simple aromaticity rules. First rule about aromaticity is the well-known Hückel's rule, or the 4Ni plus 2 p electrons, which has to do with which states clearly if you have a cyclic planar structure with n carbon atoms, if n is in the form 4n plus 2, this is aromatic, or else if it is, in other words, it's 4n divisible, it can be divided exactly by 4, it's anti-aromatic. This is a classical Hückel's rule. And the next one is less known Clar's sextet rule, where it says the aromaticity pattern with a larger number of disjoint aromatic sextets is the most important and the most favorable. And let me tell you, aromatic sextets are just 6 pi electrons localized in a single benzene ring, which is separated from the adjacent rings by formal carbon-carbon bonds. Let's be like this. This is the aromaticity pattern with 7 sextets, aromatic sextets, and the molecule in question is hexabenzocoronen. It has a pattern of aromaticity which is fully consistent with the Clar's rule. These aromatic rules, aromatic rings, can be visualized by STM. And here is a picture, an STM picture of hexco by STM microscopy. So aromaticity is just not only a theoretical concept. Okay, so we have graphene on one side, and this is the starting and the ending point. And of course, we have to have a bridge, as I said before. And this bridge, it was already illustrated. It starts with one ring, and then builds another layer. So you have 2 layers of rings, 3 layers of rings, 4 layers of rings, 5, 6, and so on. This is a sequence of aromatic hydrocarbons, which I have called main sequence, just for simple reasons. and have some special properties. And these properties can help us understand the properties of graphene at the end. So these are the PAHs, polycyclic aromatic hydrocarbons, which will form the bridge from benzene to graphene. And the first one is benzene, again. And what I have drawn here, actually, I can go back. For each one of them, I draw its aromaticity pattern. You can see here. And also a number n, which I will call the number of carbon atoms, which has a Hückel count. In other words, is this number of the form 4n plus 2, or is of the form 4l? And so as we go on, you see the first one, benzene, with L equals 1, satisfies the rule, has 6 electrons, satisfies the rule. The next one is 4L, does not satisfy the rule. But the very next, the certium coronet again satisfies the rule. So what we have a periodicity or an alteration of aromaticity patterns, and also of not only aromaticity patterns and aromaticity, because every second one, the rules of Clar and Hückel are satisfied, but for in between there are parts that that does not satisfy. This sequence, you can see it also here. If you consider any PAH, you consider as a structure, because each PAH of n includes all the other ones in the form of a babushka, in the form of a Russian doll. You see, this is a PAH. The next layer is the PAH before, and this one is the PAH before. This defines a cell structure. And I will show you that this cell structure is pretty much like the atomic cell structure. And it has some, these are the properties we want to use in order to go in the infinite limit of the properties of benzene, of graphene. So this is, I want to just remind you that the atomic cell model, it is like this. Due to the periodicity of this and the closure, the cell closure, you have the periodic element of the periodic system, and this also is verified if you draw the ionization energy versus atomic number. You have maxima here when you have a closed cell. These are the inert gases. They have a maximum here, here, and here. The same thing happens, and then the electronic configuration, you can write them in this form. Well, the geometric cell model that I showed you before, it has pretty much the same properties. Instead, here, if you, instead of the number of electrons here, that you have the Z number, here you have the number of pi electrons. And here on the vertical axis, you have a measure of aromaticity, which I have chosen here, this aromaticity index, which is called NICS, or nuclear independent chemical shift. And you can see again the maximum here every time you have a complete structure like this. So, and also this maximum, it depends on the aromaticity and also on the cohesive energy. This is the other axis. So we have a pretty much a cell model with those properties. Now, let's see again the bridge we have. Here I have again drawn the aromaticity pattern. And let's see what else we can see for this. I have here the HOMO-orbitals. The HOMO-orbitals, remember, are the highest occupied molecular orbitals. And actually there are two pairs here. I have drawn only one. But observe this one now. The first one, which is benzene, the HOMO, has symmetry G. All of them are double degenerate, but the first one is G, even symmetry, with respect to inversion. Odd, even, odd, even, odd, even. So there is a periodicity and interchange as we move, as n increases. I write like this. And the same thing is true for the LUMO orbital. The LUMO orbital has U, G, U, G, U, G, etc. And in addition, there is also a periodicity from HOMO to LUMO, G to U, U to G, G to U, U to G. So we have another periodicity here, or interchange. And also on top of the periodicity of the aromaticity that I have shown before. So I'm looking for another periodicity if there is one, and I'm concentrating here on the empty rings, not just the full ones, which are the aromatic. Observe here that the empty ring for coronet is the same, the pattern the same for the full ring of the pack before. This is, I have stressed it here by more emphasis. But also look at what happened to the next one. Now this is circumcoronet. The empty rings here with yellow are, the pattern is the same as the full rings for the previous one. And this goes on in exactly the same way. The full rings of the one pack, they have the same pattern as the empty rings of the previous one. So this gives you a trend, which is important if you want to reach a limit. Okay? And the cell model is just behind that. So what properties we have that they interchange as we move from n to n plus 1 and n plus 2? First, we have the HOMO that goes to LUMO and LUMO goes to HOMO. And we have the Gerarde go to Angerarde and EG to EU, etc. And then you have full rings interchange with empty rings, as we saw before. I have also two more periodicities here that I don't want to discuss because they're time consuming, but I just read them. They have sublattice A changes to sublattice B, and then the D3H symmetry and the other line symmetry changes from 3H to 6H, but we can see that a little bit later. And also that triagonal aromaticity pattern, circle from circle coronet, goes to aromaticity of coronet, which is hexagonal. So we still have an interchange of all of this. And all of this is motivated by molecular versus crystalline symmetry, or by inversion symmetry conflict. You see, the sublattice symmetry has no center of inversion, the molecular symmetry has center of inversion. So here, how this is accomplished in a molecular level. Here I have an arrangement of all 6 pi orbitals as they are composed by, these are the molecular orbitals, and these are the PZ, pi orbitals, p orbitals, pz orbitals, atomic orbitals, molecular orbitals. Let's watch what happens to follow. If I take the positions 2, 4, and 6 and flip the pz orbitals up, down, or red to yellow, or change the phase, in other words. So 2 goes to -2, 4 goes to -4, and 6. So what will happen if you do that? You will get this structure. In other words, also watch that 2, 4, 6 are positions, they belong to one sublattice. And by changing, just flipping the pz orbitals, molecular, the pz orbitals, you get from the BAU to BG, and also from EG to AU, and vice versa. So the molecular picture tells us that all these interchanges we saw before are a result of this, at the molecular level, of this flipping. Not of the, we are used to the flipping of the spin. And so here I'm talking about the flipping of pz orbitals, which is a different and new concept. So what happens here, I just want to show you that the molecular group, the symmetry of the molecular group, I have taken a very big part, is D6H. But the sublattice symmetry, because each second atom is different, is D3H. I have atoms that belong to different lattice, sublattices. I have colored them here with pink. So you have a pink sublattice and a dark sublattice. And the symmetry for each one is D3H. So here is the symmetry conflict between molecular and sublattice, between molecular nature and crystalline nature. And I just want to make the point here, remember that if the pink atoms were chemically different, it's not just carbon that I have labeled different, but they are different chemically. For instance, boron nitride. Now then, in that case, the molecular and the sublattice symmetry would be the same. There will be no conflict, and therefore such molecules, some structures, would not be like graphene. They could be flat, they could be hexagonal, but they would not be like the graphene. And this is true, as you will see later. Now, what happened as we go to the limit of infinity? Now, at infinity, n and n plus 1 or n minus 1 are all the same. There is no, at infinity, n plus 1 or n should be the same. So how this can happen? By a dynamical interchange, by these two opposite, like G and U, Hückel and non-Hückel, all this should coexist. And this should happen with a dynamical way. And this would be an equal a resonance, but a different kind of resonance, because we have, if we have K aromatic sextet, you have 2 to the K power, where as K goes to infinity, resonance. So this is a huge resonance, huge number of flippings involved in this one. And this is known anyway for graphene as robust electronic coherence. And the average picture of this interchange converges to the usual band structure. And this band structure has 2 electrons per ring. And I have noted like this. So this is full empty, and you have a pink all over. This is the average you can see when you have a band structure. As a result, graphene should be aromatic. It's like benzene. We can ask for that later. But graphene is almost like benzene, or I would say more like benzene. So let's summarize again. At n infinity, at the limit of the edge, when we have reached the end of the bridge. And at this limit, the HOMO, which now the valence band, and the LUMO, which is now the conduction band, should meet at some point, which is a Dirac point. And at this point, they will have a common D3H and D6H symmetry, sublattice molecular symmetry, driven by inversion symmetry competition. So Dirac points is nothing more but the fingerprints of inversion symmetry conflict, symmetry or competition. And also, this is described by many body theory as a conduction valence band inversion with opposite parities at the Dirac points, or as a dynamical breakdown of parity. You see, we have a very, very simple molecular model, and we can reproduce results which are reproduced only by many body theory or even advanced methods, which is quite good. This is why it's a very simple model with many good, very good, far-reaching results. So summary, as n goes to infinity, I have added something which I'm not prepared to discuss it here because I will go well above time, but only that for rectangular nanographenes, the Dirac points appear as edge states. But this is another story we can come some other time. These are topological edge states. Okay. The conclusion is that the competition is the molecular versus crystal competition is the driving force for the properties of graphene. These key characteristics is common not only to graphene, but to silicon, germanium, stannane, and any which they have a molecular group included inversion, which is, this is always, so they should be exactly like graphene. On the contrary, unlike silicon, hexagonal boron nitride structure, which is has a common molecular sublattice group, as I pointed out before, they are not graphene-like. In other words, they should not have Dirac points, no dimensional, four-dimensional characteristics, and in fact, they are wide gapsing conductors. And this is the structure here. In the end, I just want to leave you with a message that the molecular route to graphene is of equal importance as the end itself, like my favorite Greek poet Kavafi. You can find his poem about Ithaca here, and the translation is by Edward Keeley. Thank you very much.